In this video, we're going to discuss differentials and increments. This is a little bit controversial. It's taught in many calculus books, but I've talked to a lot of academics who love math, and they're like, what is a differential really? So bear that in mind, that some people don't like the way that we're using this notation, but it's relatively standard as well. So I'm going to show you the way I was taught. I'm going to show you based on the way people tend to interpret differentials and increments. But just know that this is somewhat controversial. Some mathematicians are like, what? You go around multiplying by dx. You know, dx is like something that's an infinitesimal. It's close to zero. It's like you're multiplying both sides by zero, and then sometimes like that's okay. Of course it is. Then you get an equation 0 equals 0, right? Wrong. In this section, we're not going to think of that as 0 equals 0. So just keep that in mind. Take this information and see it as useful. Be familiar with it, but know that some people think it's a little silly. Because we're thinking of dx and dy slightly, well, we're just thinking of them differently. So let's review what differentials and increments are from Calculus 1. Then we'll introduce the definition of a differential and an increment in Calculus 3. Then we'll talk about differentiability of z equals f of x, y. When we say a function of two variables is differentiable, that doesn't just mean that the derivatives exist. There's an extra condition involved. And then we're going to talk about approximating functions using differentials. Now, all of this is standard information, but I just want you to know it is a little controversial, some of the terminology and notation and the way we're using it. Okay, so let's go back to Calc 1 and talk about what we learned in Calc 1 about differentials. So in Calculus 1, you had a function y equals f of x. And maybe it looked like this. We would use this notation, delta x and dx. I know I said it backwards. We'd use that notation interchangeably to represent a small change in x. So let's say we're starting here at x equals x naught. And at x naught, we're at that location. That's x naught, and y is equal to f of x naught. And then we take a small step in the x direction, either this way or this way. Y is going to change. Now, the increment of y is defined to be delta y. It's the actual change in y as x goes from x naught to x naught plus delta x. So you want to know, how much does y actually change as you go from here to here? Well, you just take the final y value and you subtract the initial y value. Now, we don't normally write it like that. Typically, we say the final y value is f of x naught plus delta x, and the initial y value is f of x naught. So we're just taking those y's and we're subtracting them. We're calling that the increment of y. This is the exact change in y as x changes from x naught to x naught plus delta x. Okay, so that's the increment. Now, the differential of y was defined this way, and you use the differential all the time. Every time you do a u substitution, you use the differential. We defined the differential this way. We said dy is just the derivative of y with respect to x, or if y equals f of x, f prime times dx. So just as an example, if you have y equals x squared, well, it's a parabola with its vertex at the origin. I am having trouble with my pictures today. These do not look symmetric at all. That's okay. When x equals 1, y equals 1. The differential of y is just the derivative of y with respect to x times dx. So for this function, it's just 2x dx. Now the increment of y for this function, let's say x goes from 1 to 1.3. This is obviously not to scale, so it's going to be 1.3 squared for our y value. Delta y will be f of 1.3. That's our final y value minus our initial y value. So it'll be 1.3 squared minus 1. Guys with me? Excuse me. I hope you are. Okay. So that is the increment of y. The differential of y is just defined this way. Now, we can use the differential of y to approximate the function, approximate the change in y as x goes from here to here. So this is delta x. Sometimes we're calling that dx. And we're using those interchangeably because x is an independent variable. In this context, we're saying dx and delta x are the same thing. It's just a little change, making a little change in x. Well, if we evaluate the differential at that point x naught, excuse me, so we have dy equals f prime of x naught times dx. Now we're thinking of the differential differently. This is just a formula. This means something. This is going to give you the expected change in y using the tangent line approximation at x equals x naught. As x changes from x naught to x naught plus delta x, or x naught plus dx, because those are going to be the same thing. So this is the expected change in y using the tangent line as an approximation. Okay, well, what do you mean? Let's make it more concrete. The expected change in y using the tangent line as approximation at x naught equals 1, well, that would be using the tangent line at x equals 1 and then looking at the difference in the y value here when x equals 1 and the y value over here when x equals 1.3. So this is dy. That's the expected change in y using this approximation. The actual change in y, that's the increment. That's this difference. That's delta y. Okay, so for this particular example over here, when I evaluate my differential at x naught equals 1, so this is 2x, that's my slope for y equals x squared. I'm evaluating it at x equals 1. This is saying, plug in 1 for x. What this is saying is, change x by a little bit. Well then y, I would expect y to change by 2 times that little bit. So if x changes by delta x equals 0.3, so x goes from 1 to 1.3, then using the tangent line as an approximation, I'd expect y to go up by 6, because I'm just taking that 0.3 and I'm doubling it. So let me write that down. As x changes from 1 to 1.3, the expected change in y is dy, and that's going to be 2 times x final minus x initial. So 2 times the change in x, which is 0.6. Now you might be saying to yourself, well, how does that compare to the actual change in y? Well, what's 1.3 squared, guys? I think it's 1.69. If I do 1.69 minus 1, I think that's 0.69. So here is the actual change in y, and here's the expected change in y. We're still off by 0.09. So that's 9/100ths. That's pretty large, actually, but that's because our step size is so large. We're going from 1 to 1.3. If we had a smaller step size, this would be a better approximation of the actual change in y. So let's go through those definitions again, and then we'll talk about how this generalizes to functions of 2 variables. So when we're discussing increments and differentials in Calculus 1, the differential of x and the increment of x are the same thing. We're thinking of them as representing the same value. Both of them represent a small change in x. The increment of y is the exact change in y using the function, saying, how does y change as you go from x0 to x0 plus delta x? Well, I just take the final y value and I subtract the initial y value, so that's that minus that, and that gives me the increment, or the exact change in y. Now the differential of y was just defined to be this. We're just saying dy is its derivative times dx. Those are the same thing. So we're good to go there. And then when we evaluate that differential of y at a particular x value, it represents something. It represents the expected change in y using the tangent line approximation to the function at x0. As x0 changes, or as x changes from x0 to x0 plus dx, or x0 plus delta x, because we're treating that dx and delta x as interchangeable, like we did here. So here in our example, that's our f of x, it's x squared. Here's the differential of y. Here is the exact change in y as x goes from 1 to 1.3. And then here is the approximate change in y as x goes from 1 to 1.3 using the tangent line as an approximation. If x goes up by 0.3, I'd expect y to go up by 0.6. And it looks like that's pretty reasonable. Okay, so that's Calc 1. Let's look at a Calc 3 version of all of this. I bet you can imagine where this is going. In Calculus 3, rather than using a tangent line to approximate our function, we've got a function of 2 variables, z equals f of x, y. We're going to use a tangent plane to approximate our function. And that's at some point x0, y0. Okay, so now in this context, when we're talking about increments and differentials for z equals f of x, y, and if you are cringing at the fact that dx and delta x are the same, that's where this is controversial. A lot of people are saying, that can't be the same thing, but that's how we're using it in this context. Bear with me. It's just notation, and it's all about how you interpret these expressions. And some people disagree with this, but it's pretty standard, so you should be familiar with it either way. In this context, x and y are independent variables, so dx and delta x are going to represent the same quantity. It's just a small change in x. So x could change by a little bit from x0, y0. And y could also change by a little bit. So delta y and dy are going to be the same thing, and they represent a small change in y. Well, as x and y change from x naught y naught to x naught plus delta x and y naught plus delta y, z is going to change. The exact change in z is called the increment of z. So we're going to represent that by delta z. This is the exact change in z as x goes from x naught y naught to some nearby point, x naught plus delta x and y naught plus delta y. So we're just going to do z final minus z initial. So that's f evaluated at the new point. Oops. Minus f evaluated at the original point. Okay, that's our delta z. Now the differential of z is defined to be this. Remember what the differential of y was? It was the derivative times dx. The differential of z, or this is sometimes called the total differential of z, or sometimes you'll hear it called the exact differential of z. If you've already studied exact differential equations, then you've seen this before. It's given by this. dz equals the partial of f with respect to x times dx plus the partial of f with respect to y times dy. So this is the change in z as x changes times a small change in x. So you get some change in z due to that part. And then this is the change in z as y changes times a small change in y. And you get some change in z due to y changing. If you want the change in z, you just take this change and this change. This is provided that the function z is differentiable, and we'll talk about what differentiable means in a little bit. Okay, I got a little bit ahead of myself. This is just the formula for the exact differential or the total differential of your function. So let's calculate this, and then we'll talk about what it means. Excuse me. So here's an example. Let's say z equals x cubed plus 3xy squared. Well, then I could write this lots of different ways. I could write this in subscript notation. That's the partial of f with respect to x times dx plus the partial of f with respect to y times dy. Or since z is a function of x and y, I could say the partial of z with respect to x times dx plus the partial of z with respect to y times dy. Any of those is fine. I'm just going to use this notation here because of the way I've written this here. So I want the partial with respect to x. Well, the derivative of x cubed with respect to x is 3x squared. And when we take the derivative of this term with respect to x, we're treating y as a constant, so we can bring down the negative 3, we can bring down the y squared, and then we take the derivative of x with respect to x, that's just 1. So we just get 3x squared minus 3y squared. And the partial of z with respect to y is this. There are no z's here, or excuse me, no y's here, so it's a constant with respect to y. The derivative of a constant with respect to y is just a constant, or excuse me, just a 0. Derivative of a constant is 0. And this is a constant times a function of y, so we bring the constant down, and then we take the derivative of y squared with respect to y, which is 2y. So we get negative 6xy. So we put those pieces together. The total differential of z is 3x squared minus 3y squared, that's the partial with respect to x, times dx, plus the partial with respect to y, adding a negative is same as subtracting, times dy. So this is f sub x or z sub x, however you want to represent it. Partial of f with respect to y or z sub y, same thing. That's the total differential of z. Okay. So if someone asks you for the total differential or the exact differential of z, this is what they're asking you for. It's the derivative times dx, or the partial with respect to x times dx, plus the partial with respect to y times dy. You might be saying to yourself, what does this mean? What does this mean? Well, yeah, we'll talk about what it means in just a little bit. Now let's say you take this exact differential or total differential and you evaluate it at a point. So now you've got dz equals the partial of f with respect to x times x, or evaluated at x naught, y naught, times dx, plus the partial of f with respect to y evaluated at that point, times dy. So this is a number times x plus a number times y. Remember what happened when we plugged in a point over here. We said this is the expected change in y using the tangent line to approximate the function when x changes by dx starting at x naught. So x is starting at x naught and now x is going to be at x naught plus dx. And we're saying, okay, well how much does y change under those circumstances? Using the tangent line as an approximation. Okay, the Calc 3 version for a function of two variables is that this represents the expected change in z using the tangent plane as an approximation. And I guess we're using the tangent plane at a particular point, at x naught, y naught, as an approximation. When x changes from x naught to x naught plus dx, or x naught plus delta x, because we're using those interchangeably, I'm sorry. And y changes from y naught to y naught plus dy, or y naught plus delta y. So it's a change in z using the tangent plane approximation at a point. All right, so let's use this function and evaluate this at a point. So let's say we're at the point x equals 2, y equals 3. We'll have the differential of z is 3x squared minus 3y squared, evaluated at xy equals 2, 3. Or you can call that x naught, y naught equals 2, 3, that's fine, times dx, plus negative 6xy, evaluated at 2, 3, times dy. I think I'm going to factor out that 3. So I have 3 times x squared minus y squared times dx plus negative 6 times x times y times dy. Just doing arithmetic now. 4 minus 9 is negative 5. And that's negative 6 times 6 is negative 36. Whoa, z changes by a lot. Look at those slopes in the x and y direction at that point. The slope in the x direction at xy equals 2, 3 is negative 15. So if x changes by a little bit, the z values are going to go down by 15 units for every 1 unit change in x. So if x changed by 0.1, z would go down by negative would go down by 0.1. Z would go down by negative 1.5. And the slope in the y direction is negative 36. So z would go down by 36 units for a 1 unit change in y. So if y changed by a little bit, you get this slope times that change in y. So this is the change in z as x changes by dx and y changes by dy starting at this point 2, 3. Now if somebody asks you to approximate the change in z using the tangent plane as an approximation, at the point, let's say 1.9 and 3.05. Well, that's a new x value and a new y value. That's a little bit less than 2. That's a little bit more than 3. Then I would take these new x's and y's and I would find the corresponding change in x and change in y, and then I would substitute those into the formula over here. Okay, so dx, that's my change in x, is just x final minus x initial. Of course, I think we can all see if we started with x at, or if our new x value is 1.9 and our old one was 2, x just went down by 0.1 units. And y, or the change in y, is just y final minus y initial. Our final y value was 3.05, our initial y value was 3, so y went up by 0.05 units. So using these as our change in x and change in y, our z value would be expected to change by this much. We take negative 15 dx minus 36 dy, and we substitute. And then we see using these values how much z has changed. Okay, I'm using a calculator for the arithmetic. Don't make fun of me. Too late, I know, it's okay. And I get negative 0.3. So I just don't want to make an arithmetic error on here. Okay, it's always good to check. All right, so this is my expected change in z using the tangent plane approximation as x goes from x goes from 2 to 1.9 and y goes from 3 to 3.05. You might be saying, okay, well, what is that really? Well, if I go negative 0.1 units in the x direction, and the slope in the x direction is negative 15, because I went backwards, the z values went up by 0.15. Now over here, the slope in the y direction was negative 36. And I'm taking 0.05 times that. So it looks like my y, as y increases by this much, the z-values go down by this times that. So the z-values go down by negative 1.8. So let me just break that down a little bit. So my x's cause the z's to go up by 1.5. My change in y causes the z-value to go down by 1.8. And then the total change is just the sum of those two changes. And so we get negative 0.3. So this is just an estimate. This is the expected change in z. Using the tangent plane approximation, at x naught y naught equals 2, 3. Now if somebody asks you for the approximate z-value, you could say, well, my z-value is approximately equal to my original z-value, my initial z-value, plus the change. So my initial z-value is my function evaluated at the point 2, 3, because that's my base point. That's where I've drawn my tangent plane. And then I want to take that value and I want to subtract 0.3. Now the function this time was x cubed minus 3 times x times y squared. So we want to evaluate that at 2, 3 and subtract 0.3. So I've got x cubed, that's 27, minus 3 times, oh gosh, I plugged in the y value for x. That's wrong. So I've got x cubed, that's 8, minus 2, or 3 times x. 3 times 2 is 6, so I'm subtracting 6. 6 times 9, that's 54, minus 0.3. So I end up with, what's that, negative 46, minus 0.3, so negative 46.3. That's my approximate value of z at 1.9, 3.05. That's the approximation using the tangent plane. I could have also just found the tangent plane and then plugged in those 2 points and I would get that approximation as well. But we're studying differentials, we're studying their interpretation when we evaluate the differential at a point. Okay, now you might wonder to yourself, how good is that? How good is that approximation? Well, we could always compare it to the actual change in z. So or the actual z value at that point. So let's find z at that point. So f was x cubed minus 3 times x times y squared. So I have 1.9 cubed minus 3 times 1.9 times 3.05 squared. And so I've got 1.9 cubed minus 3 times 1.9 times 3.05 squared and I get negative 46.16525. Let's subtract negative 46.3 from that. Look at the difference. So we're off by a significant amount. We were off by 0.13. So it's not an excellent approximation, but it's pretty good. Pretty good, not bad. Okay, so recap. What does all of this mean? We're talking about differentials and increments. Differentials, dx and dy, when we're talking about functions of two variables. Delta x and dx and delta y and dy are being used interchangeably. We're saying we're making a small change in x and we're making a small change in y. What happens to z? What happens to z is this increment of z. What's the actual change in z? Well, to find the actual change, I find z at my new point and I subtract z at my old point. That's represented by delta z. That's the actual change or the exact change in z. Okay. Then we said, okay, what is the exact differential of z? Well, the exact differential of z is this. It's just the partial of z with respect to x times dx plus the partial of z with respect to y times dy. It's just like that differential from Calc 1. If we have a function of one variable, we just take the derivative and multiply by dx. Function of two variables, you take the partial derivatives, you multiply by dx and dy, and you add them. Okay. It's just a formula. You substitute. And you say, well, what is the total differential at a point? Well, that's when you've got this base point. That's where you're creating your tangent plane at x naught, y naught. If you substitute that in here, and you substitute that in here, that x naught, y naught, into those partials, you're getting a slope in the x direction times a tiny change in x, plus a slope in the y direction times a tiny change in y. This is giving you a change in z as x changes, and this is giving you a change in z as y changes. The total change in z as x changes from x naught to x naught plus delta x, and y changes from y naught to y naught plus delta y. When x and y change like that, when we use the tangent plane as an approximation, we're saying dz is given by this. So this is when I evaluate the differential at a point, it represents the expected change in z using the tangent plane approximation at this base point, x naught, y naught. As x changes by dx units and y changes by dy units from that base point. So x is going from here to here, y is going from here to here. So you plug in the base point, that's where you're drawing your tangent plane, and it gives you a formula for the change in z as x changes and y changes. Now if they ask you for the change in z as x changes and y changes from that base point to a specific new point, well, you have to find the change in x and change in y, just taking x final and x initial and subtracting them, and then substitute over here. So this is the approximate change in z using the tangent plane as an approximation at the new point. So dz, that is the negative 0.3 in this example, that's the expected change in z using our approximation at that point. Now we go down further. Well, what if somebody says, I don't want the change in z, give me the new z value approximately using the tangent plane approximation? Well, then you just take the original z value, the initial z value, the z value at the base point, and then you add the change. So this time, our function was negative 46, and then we changed by negative 0.3 according to the tangent plane approximation. So z would approximately be this negative 46.3. Okay. So that is how we interpret differentials. That's what the exact differential is, and that's what the total differential is when we evaluate it at a point. It's an expected change in z using the tangent plane approximation. Now this is always provided that our function is differentiable, and I think I'm going to leave differentiability for the next video. So we'll talk about exactly what it means for a function to be differential there. Now there's one more thing that I want to show you, because many of you have either recently taken differential equations or are about to take differential equations. In differential equations, you're going to solve something called an exact differential equation. And I'm going to use a very simple surface because it helps us understand the concept a little bit. So let's say we've got z equals x squared plus y squared. It's always good to start with simple examples and then generalize to things that we'll have to imagine and that we can't see. It can get abstract after we get concrete and we wrap our minds around it, right? So here's our function z equals x squared plus y squared. If z equals a constant, let's say z equals 4. Well, then we're just on this surface. We're up 4 units. And we're on a circle of radius 2 that's elevated 4 units from the xy plane. Now, if we take the differential of both sides, so this is z equals 4, and now I'm taking the differential of z on this side and the differential of 4 on this side. Well, this is partial of z with respect to x times dx plus the partial of z with respect to y times dy, and the derivative of 4 is 0. In this case, partial of z or f with respect to x is just 2x. The partial of z or f with respect to y is 2y equals 0. This is what's called an exact differential equation, because this is the exact differential of this function z equals x squared plus y squared. Our goal when solving an exact differential equation is to go back. It's to find this equation, or let's be more specific. We're actually trying to find this equation, x squared plus y squared equals 4. But we're thinking of it differently. We're thinking of this x squared plus y squared equals 4 not as a circle in the xy plane, but we're thinking of it as a level curve of this function z equals x squared plus y squared. In differential equations, you start with something that looks like this. And your goal is to go backwards. The question is, what is the original formula? F of x, y equals k. What is that f of x, y that you had to take the exact differential of to get this on the right-hand side? And of course, the derivative of the constant is 0. Now, most of the time in differential equations, your exact differential equations don't look like that. That one's really simple. You might start with something that looks more like this. And this one's still pretty simple. You'd have 3x squared minus 3y squared dx minus 6xy dy. Instead of the dz being over there, you'd say equals 0. And the question is what is z equal to? And z equals a constant is the solution of the differential equation. So what we're really looking for when we're solving an exact differential equation is this level curve of this function of 2 variables. Now, I will let your Diffie teachers teach you more about that, but I just wanted to show you the connection between the exact differential, which we just studied, and a very important method that you'll study in differential equations called methods for solving exact differential equations.